¿Qué tal? Buenas tardes. Muchas gracias por asistir. El día de hoy tenemos la visita del doctor Torsten Braun, I hope I pronounce it well, que es el jefe del grupo de investigación en comunicaciones y sistemas distribuidos de la Universidad de Berna. Un poco de sus antecedentes. Ha sido el director del Instituto de Ciencias de la Computación en la Universidad de Berna. También ha visitado varias instituciones como Faculty Visitor o Research Visitor en los laboratorios Bell en Nueva Jersey, también en la Universidad de Lancaster, en la Universidad San Carlos de Sao Paulo en Brasil, en el INRIA, en la sede europea de IBM en Heidelberg. Entonces, es una persona que trabaja mucho en sistemas distribuidos. Y pues sin más, bueno, también ha sido vicepresidente de la Fundación Switch, que es una fundación que tiene como misión permitir, mantener, promover la investigación segura y networking en Suiza, además de crear o mantener la infraestructura educativa. Y pues listo, you are, perdón, perdón, ya me atoré. Muchas gracias por estar aquí. The audience is yours.
Ok, muchas gracias por la invitación y muchas gracias por venir y por tu interés. Pero ahora tengo que hablar inglés, since my Spanish is very little. Also, I have a Spanish-speaking wife, but she didn't teach me yet enough Spanish to give the talk. Okay. Yes, thanks also for the. Today, I've entitled my talk Distributed Machine Learning in the Internet of Things. But before going to the topic, I also want to discuss what else we are doing. Maybe you are also working in similar fields, and maybe we can also establish some kind of collaboration. But basically, the talk today, the scientific part where I go a little bit deeper, was mainly shaped basically by these two PhD students. So these PhD students are still in our group. So it's on the left, Eric Samikwa, who came with a master's from KTH in Stockholm. And the other guy, Lucas Pacheco, it's a little bit a special situation. Also, I want to show what is possible with us. So basically, he's a student, or he was a student at UFPA in Pará in Belém, in Brazil. And with that university, we have a so-called joint supervision PhD program. That means that the student is supervised by two supervisors. So in that case, by Eduardo Saqueira in Brazil and by me. And the student is then spending the time partly in Bern and partly in Brazil. So in this case, the home university is Bern for some reason. So most of the time he has been in Bern, but part of the time he is now in Brazil, but he's co-supervised by two supervisors. So that's a possible collaboration which is possible in our university. Then our PR department usually asks us also to do some PR. So they have created this slide to give you some details. When I came here, I thought we are a big university with nearly 20,000 students. Now I learned you have some 300,000 plus students, so we are pretty small compared to you. We have, as we have a bachelor program, a master and a PhD program. The bachelor program is taught in German, since I'm in the German part of Switzerland. But the master program and the PhD program are all English. That means PhD program, we don't have any courses, so we only focus on research. So if a PhD student comes to us, he or she immediately begins with research, since we require a master for entering the program. We are not focusing on computer science. Bern is more well known for physics, climate sciences, and also medicine. But what we see in the recent years is that more and more disciplines also apply computer science techniques, in particular data science. Everybody knows that. Therefore, we are more and more supporting also other disciplines in the research. I will give a few examples. So then I try to describe a little bit our structure. So in total we have 8 faculties. Our faculty is Faculty of Science, and Faculty of Science has 5 different sections. Let's say we are in the section of mathematics and computer science, and there was one guy who also was at University of Bern some time ago, and this guy submitted a thesis, habilitation thesis we call it, and interestingly the thesis was rejected in the first attempt. I don't know exactly what was the reason. Either the thesis was not good enough, but it was including the relativity theory already, or people didn't understand. So either or. So you can decide what have been true. And I also say it shows our quality standards. Of course, joke. Then in computer science we have certain areas. Usually we have a group which is headed by one professor, and I'm heading this communication and distributed systems group, so where we mainly do some networking research, but in recent years all the disciplines were influenced by machine learning, by data science, and also us, of course. But we are not doing too much research in new machine learning algorithms. We rather look how machine learning can be distributed across various devices, and also have a look on the networking aspects that are coming up there. Now, this is an overview of what we are doing in our research group. And of course, we are also heavily dependent on funding. So we have, for example, the Swiss NSF, Swiss Science Foundation, National Science Foundation, and there we have 2 projects currently running: Intelligent Mobility Service and Immersive Communications. You see here the number of PhD students working in each of the projects. I will have a slide for each project later. Then we have some free research. That means I have some funding from university where I can hire some PhD students. And today's topic is mainly shaped by the PhD students in that area. Then I mentioned we have more and more interdisciplinary research where, for example, geography people are coming to us and have some requirements, or even psychology people come to us and ask us to help them to do their research. I will also talk about that. And also I have 2 industrial PhD students. They are hired by a company, by a pharmaceutical and electricity company, and they do their research mostly at the company, but then they come sometimes to university to discuss the further development. And these are the topics here which are not so close to our networking topic. So this slide gives an overview of the 2 projects we have funded by the Swiss National Science Foundation. The first is distributed positioning, and in particular for indoor positioning. So for example, what we could do now, we could try first to count how many people are in the room. Usually everybody carries a smartphone, and then we could also find out how the people are here positioned. And as you know, indoors you cannot use GPS since the signals don't make it. Therefore, we need other mechanisms. And what we do here is that the wireless devices are exchanging information. So in that case, you can roughly estimate the distance between these two devices and these two, and so on. And if you exchange all the information, in the end, you can determine the position of each device. And currently, it very much depends on the wireless technology you use. We do it, we support Bluetooth, we support ultra wideband, but we are pretty much in an accuracy area of below 1 meter. So we could roughly determine who is sitting where in this room, for example. Another project which is now coming to the end is federated learning for mobility prediction. That was some years ago inspired by a European telecom operator who came to us and said, we have a little bit of money. We are looking for some good idea where we can apply machine learning in telecommunications. We don't know what to do with machine learning, but we have the feeling we have to do something with machine learning. And then we thought about it, and what we suggested to them is, what you could do is with machine learning, if you have the amount of data, of movements, of connections of users to base stations, and so on, what you could do is you could predict where the user goes next. So if a user is at a base station, then you could predict whether the user goes to the next east base station or next south base station, and so on. And that could also help the telecom provider to better manage the resources. So if the telecom provider knows where most users will be at a certain time, then frequencies or computing power can be allocated. Also handover can be better supported. So if, for example, the network provider knows I will go next in the next few minutes to this base station, then the resources can already be allocated for that. And the handover can be done more quickly. And there we use the federated learning. I will later talk about what federated learning means. And the prediction accuracy with the data we got was already in the range of 70 or 80%. That means 80%, in 80% of the cases, the network provider can guess where you go next. That's was quite some interesting result we achieved. That's a recently started project called Networking for Immersive Communications. So the idea there is in future we might have more and more virtual reality applications or augmented reality applications. And in particular, in virtual reality, you have either a head-mounted display or some glass, and then the video is projected to the head-mounted display. But what happens then is if you move your head to the left, then the video from the left should be immediately displayed. And now it's not just a movement left or right, but also up and down or even backwards. That means what usually you are doing, you have a 360-degree video, which requires much more bandwidth than what you have today for high-definition TV, for example. And in particular over wireless networks and mobile networks, you don't have that bandwidth that you can simultaneously stream from all directions the highest quality. So what usually is done is that the systems often try to predict where you are watching, in which direction. So if, for example, if you can predict that you continue to watch straight or a little bit to the right or a little bit to the left, then you only have to stream the videos from these directions with high quality. And maybe for the unlikely case that you completely turn around, maybe you have a lower quality stream. So in that case, you can decrease the bandwidth. But that has to be this decision has to be very quickly, and you have to detect the movements so that you can stream the video. So in those virtual reality applications, you have first the demand of high throughput and low delay, and that is quite challenging to support. So in that case, we need this viewport prediction and low latency communication support. For example, what you can do is you can try to cache some data, the data which are most likely to be transmitted or to be received. And also we have a look on mobile scenarios where you might walk in a larger environment, in a virtual environment. Then network softwarization is another topic we are investigating. So formerly a mobile network was built out of hardware boxes. Today network operators are trying to push all the functions into a virtualized environment, into the cloud or in other softwareized environments. So you might have heard about this Open RAN initiative where 5G network is completely implemented in software, basically. And what one student is doing, it's also related to VR. He tries to decompose the processing for VR into certain functions and then distribute the functions across various devices. So to do load balancing and provide the computing power which is needed for such an application. Then network slicing means that basically you have different communication stacks for different application areas. For example, for TV streaming, you might have a stack. You might have a stack for IoT communication or for other applications. And so in that case, basically you separate your software system into different slices, and you also have to do some resource allocation for that. This is now a project where I don't have a single PhD student working on, but we are supporting our geography people. And they have the following problem. So this is a map of Bern. Bern is tiny compared to Mexico City, 150,000 people living there. There's a city center, mainly brick, stone, asphalt. And 5 kilometers away, you're already in the countryside, everything green. So now these are a few measurements of the temperature during a heat wave in 2019, summer. So we see we had even 36, 37 degrees in Bern, which is not very frequent, maybe a few days a year. But what happened there is, while at the countryside during the night, the temperature dropped to 20 degrees. At around 11 p.m. in the city center, the temperature still was at 30 degrees, just because of heating up all the bricks and so on. So this is so-called urban heat island effect. And of course, the heat is not good for the people. In particular in Bern, we don't have air conditioning and so on. And now the geography people, they want to find out what are good design patterns, how to design cities. It means in terms of using the material to have more green areas, maybe even watering some areas. Also, you can construct the city in a way that there's more wind blowing through the city and all these things. Now, what they wanted to have is they wanted to have a more dense deployment. So we designed and manufactured a new kind of sensor for them. It costs us about $100. So with that, 300 sensors means $30,000, which is still manageable. And the problem they had now was the following. This was the design of the sensor. The sensor is somewhere in between, but it was protected by these plastic bowls. So basically you can buy these things at IKEA for $1 or so. The problem they had then, so they had to shield the sensor because of the sun and other snow, ice, whatever. And the problem then was during sunshine and heat, the temperature value inside was not correct anymore, since the air was heating up and was therefore not correct anymore. And what we did now was we implemented the fan, which just blows out the air, blows the air out for 2 minutes, and then we do the measurements, and then it was pretty much correct. And the problem, however, was in the end, 98% of the energy was used by the fan. And yeah, we had to come up with a solution. We then had some solar panel, which was enough. But then we had together the following idea. I always say, if you have a problem and you don't know how to continue, you have to think about machine learning, and that's what we also did here. Here you basically see what happens if the fan starts to work. So we have a temperature of 22 degrees, and then the fan starts to work, and then the temperature here goes down and down and down, and then here is more or less even here. So we have a steady state here. So basically what we are doing now is the following. We start with a fan, measure what is going on, then we stop here, and then we try to predict where we end up. And of course, all the data can be used for machine learning, for training the model. And in the end, here, this point basically was the predicted value, and here this is a real curve. So in the end, we see we are not too far away. If we just stop here the fan and just take the initial curve, and then we can basically predict here what will be the final value. So in this case, if we stop here in the middle, we save half of the energy, simply said. So that's also something we have developed for our geography people to help them to do the research. Another project which is currently supported by our university, you know for sure that a big buzzword is digitalization these days, and all the disciplines use more computer science methods, data science methods, programming skills are needed, and also data collection and machine learning is needed. And the same with our psychologists. What their problem was is they had a couple of research groups, and one research group was interested in finding out the characteristic and the feature of a person. And the idea was, give each person a mobile phone, and dependent on how you use a mobile phone, you can tell what kind of character is behind the person. One example was, or they said, for example, how you swipe over the display can tell you something about the person. Or, for example, how much active you are can tell you about the person, whether you're lazy or not, and so on. For my environment, I came up with the idea to measure the energy level of the phone. For example, I consider myself, maybe I'm wrong, but I consider myself more organized as my wife. And usually when we leave the house, my battery is charged and her battery is not charged. So things like that you can use then for characterizing the people. And what did here, we implemented an application which tries to get all the data you can get from your phone, be it an Android or an iPhone. I have to say, with iPhone it's much more difficult because iOS has stronger restrictions than Android. But in the end, we implemented what we could do, and now the psychology people give the app to the students. The students get either a little bit of money or some credit point, depending on the cases. And then they get monitored and provide the data for the psychology researchers. And then they want also to characterize a person, but they also want, for example, to identify whether a person becomes more stressed over time or whether the stress level rather goes down and such things. Also, they want to find out the relation between stress and nutrition, how people eat and drink, and all these things. But we focus on our computer science things and let the psychology people then do their work with the data we are providing. Okay, so this basically was the overview of what we are doing, and now I want to go a little bit into more scientific detail. Topic: machine learning in the Internet of Things. So of course, there are plenty of example applications where machine learning can be used in health, psychology. We have seen local energy systems. You want to monitor your devices at home, how much energy they produce, or how much energy they consume. Building control. You measure temperature, maybe oxygen level, and then control the building in order to reach the target values. And often you can do a lot with machine learning. You can do often prediction how the situation will work. For example, you can simulate what will be the effect of opening windows or starting certain devices in the house, and how the climate in the building will then evolve. And so in such scenarios, we have more and more sensors that are carried by humans, and sensors which have been deployed in a building, or also somewhere in a city where we have more and more smart cities, for example. The problem, however, with machine learning on IoT devices is that the IoT device, the sensor, is typically a simple device, has a small processor, small memory, limited energy, and so on. So you cannot just run the machine learning, the training process on these devices. That means you can do it. There are also some mechanisms to generate simple models, but then that's at the cost of accuracy in the end, of course. And you want to have accurate predictions, and therefore you need certain processing power and also storage to store the data. So what you can do then is you can just collect the data on the IoT devices and just transfer everything to a server where you store everything, where you train everything, and then you can do some prediction, and maybe also you then have to send some signals back and give some feedback to the IoT devices in order to control certain environmental processes. So if you go this way, just transmit all the data to a server, then you run into two problems. We do the same currently with a psychology case, and there basically we send all the data from the phone to a central server. That means if one person would get access to the server, then this person would know quite a lot about the students. Yeah. So that means if you transmit all the data to the server, you have a privacy issue. Yeah. The other problem is the raw data can be quite huge. For example, movement data or heart rate data, where you have a lot of data within maybe a minute or a few seconds even. So this is could be a significant data stream. So this could end up to saturate maybe a wireless network, depending on what kind of technology you have. So just blindly transmitting everything to the server might be not the best idea. And the approach, what we are trying to investigate now, is we also want to make use of the IoT devices. The IoT devices, they have CPUs, some of them have GPUs already. They have a certain amount of storage, so why not already use such resources of the IoT device? And in order to support that, certain distributed machine learning mechanisms are evolving. Some of you might have heard about federated learning or split learning. I will try to explain what that means. And in the following, I briefly want to go now through 5 publications we produced in that area of distributed machine learning in the Internet of Things. So the first is called adaptive early exit of computation. And basically what we are doing now, we try to distribute the processing of the model. We don't distribute the learning there, but we take the model and distribute it between a server and the IoT device. But we want to do that somehow dynamic, not in a static way, but in a dynamic way, since typically a wireless network also might change the characteristics. So you might have a high bandwidth at some point of time, and then you go to another area. Maybe you have a longer distance to the base station, then you have a lower bandwidth, for example. So the situation in a wireless network can be dynamic, and therefore we wanted to come up with a dynamic adaptive scheme. So the basic idea is we might have different levels of computing, a cloud server, an edge server, that's basically a cloud server which is at the edge of the network, and then the IoT device, and then just distribute the machine learning model among the different levels. So basically what we have to do, we have, for example, we have to take a neural network and we have to cut it and put one half on the server and the other half on the IoT device. That is the simple idea we try to follow. However, we also want to consider the energy. If we would put the whole model on the IoT device, even if it would fit, maybe the IoT device would run out of energy soon. And the other issue is also latency, since we always have a round-trip communication, and it means signals are sent from the IoT device to the server and back. And that adds some latency, and we want also to minimize this latency, basically. So this is, again, the simplistic illustration of our approach. We have some input at the device. That means some data. Then we have parts of the machine learning model on the IoT device. Typically, we have some layers in a neural network. So part of the layers are processed on the IoT device, and other parts are then processed at the server at the edge of the network, and then we create here some output. And the question we are now investigating is whether we have to cut here or whether we have to cut here. That means the so-called point where we cut the model into two pieces. And this is the approach how we come up with this optimal partition point. So in this case, we cut here. This is a partitioning point, and that could be here, here, or here. And basically what we are doing, we are observing the characteristics of the network, mainly the bandwidth. We are estimating the processing time of the various levels or layers of the neural network on the server and on the IoT device. That means we have values for processing on the IoT device and on the server, and everything goes into an optimizer, and the optimizer then calculates the optimal point for partitioning the model. So here are some formulas. Basically, here we model the energy, which depends on the energy for communication, this term, and the energy for computing on the IoT device. We don't care about the energy on the server. And here the latency consists of the latency for computation on the IoT device and the server, and for the communication delay. And then we try to optimize and find the best partitioning point. So everything we developed here has also been implemented in our lab using some Raspberry Pis and some desktop computer. And here are some typical models, and from which are mainly used for comparing also different machine learning works. And basically, here we see now the prediction latency and the energy consumption based on whether we split after the first layer, second layer, third layer, and so on. So we see here we have up to 22 layers. So we used this model here. So we see here the best choice is cutting the model into two halves after the fourth layer. Then we have both the best latency and we have the lowest energy consumption on the IoT device. Then the next step was the so-called DisNet approach. So in the previous approach, basically what we can do is we can cut here the model into different parts based on so-called horizontal partitioning. So basically the cutting is done horizontally. And now what you also can do is you also can do vertical partitioning. That means not just here horizontally, but also vertically. And that means that part of the data goes to the left part, some to the middle, some to the right part. In reality, you have an overlap of the data. You cannot cleanly cut, but in the end, some of the data here at the border has to go to the left and to the middle to support here the model processing. But in the end, so if you take this picture, rotate it, we end up here. Now we have both partitioning methods. So here is, since we have rotated the horizontal partitioning, this is vertical partitioning, but we have rotated because of the slide layout. And then in the next step, basically we assume that we have a kind of sensor network or wireless network consisting of different devices, maybe also heterogeneous devices. Some devices are more powerful than the others. And now the task is basically to map these blocks here to the different devices. So one block or multiple blocks might run here, one here, and so on. So that is now even more complex optimization task to come up with a good allocation for this horizontal and vertical splitting. So this could be one example how these different layers, how these blocks are basically assigned to the different IoT devices or computers we have here available for the processing. That means the input data is distributed, and then we have some output data here after this model processing. Again, we have to optimize then the best allocation. That's also not quite trivial. So again, what is important is the energy and the delay in the end. So we evaluated everything this time using Raspberry Pis and Jetson Nano to have some heterogeneous devices so that we are not in a homogeneous case. And then we found out that our approach is performing better in terms of delay and also in terms of energy consumption on the IoT devices than other competing approaches we have found in the related work. So far until now, I only talked about the model inference, not about the training. So the training was always done before and was done centrally. So in the next step, now we are looking in also distributed learning, where the machine learning itself is, the training is also basically distributed. And before I come to our approach, I just want to introduce the main concepts which have been known from literature. Maybe some of you are also working in federated learning. Is somebody working on that? Not yet. It's an extremely crowded research area. You have to be very careful if you go there. But it's very, very popular. So what is federated learning about? So basically, now this is a general scenario. Clients could be computers or of mobile phones, for example. That means I could run a machine learning process on my mobile phone, learning some parameters I know about my behavior or environmental issues, for example. And the idea is now, also another example I will discuss later is vehicular networks, cars, where maybe cars are learning themselves, but then the idea is to share the knowledge to others. And basically what is happening there is that each client, for example, each individual car might do some learning. For example, how the driver behaves or how other drivers are behaving and so on. And instead of just keeping this knowledge local, we send it to a server. And then the server is collecting the data, the model parameters from all the cars, and then tries to come up with an even better model. And the idea is the more data you can provide for the learning, the better should the model be. That's the basic idea. That means in that case, the various clients are sharing the data to the server. The server can do some simple averaging of the model parameters. So typically we have the same network type, but for example, weight might be different here at the different clients. So in that case, the weight parameters are sent to the server. The server does some averaging and sends back the averaged values to the individual client. So in that case, all the clients can come up with better models. However, there are always some problems. For example, there's a problem of so-called stragglers. That's in particular valid in IoT environments. That means in order to run this process, you should assume that each client permanently sends the data, and then everything can be received, processed, and distributed. The problem might be now if, for example, this client is a low-performance device, and maybe the network is even slow, then it might always take some time until this device comes up with the model parameters. While these two clients already have submitted the data, this one is always behind and late, and then the server has to wait until everything has been collected. This is called a straggler. That's a problem in this federated learning approach, which of course many people also are currently investigating. Then in a networked environment, we have different throughput. For example, we might have a high throughput link here, so this first client could send the data quickly, while we have a low throughput link here, so it takes some time until the data is sent to the server. And energy consumption might be quite considerable for the training and also for the communication. So the amount of data you have to communicate here is not negligible, and communication in the Internet of Things can be quite expensive then. So all these things have to be considered when you come up with a federated learning approach. So now, the other concept we already have seen in a similar way is split learning. Basically, it's similar to this separation of the layers, but now the learning is also integrated here. So in this case, we basically split the network again into halves, but run now also the training on the IoT device and on the server. So in the simple case, if we have 3 clients, we just cut the model for each client at the same level. Then each client here has the same part, and the other part is trained here at the server. However, this does not consider the heterogeneity of the devices, since some device might be able to process even more layers, others have not enough resources to train a few layers only. So we wanted to solve that problem of device heterogeneity, and also again network conditions could become heterogeneous. And basically that's what my PhD student came up with. Basically, we want to have a system where the edge server is always training the upper layers and the IoT devices, the lower layers. But now the IoT devices could be heterogeneous, have different computing and storage resources. So maybe one device could be more powerful and cover more layers than the others. So in that case, we cannot have this homogeneous split point here, but we have to come up with individual split points for all the devices. And again, we have to optimize energy, we have to optimize the time for training. Since basically that I forgot to say here in split learning, we have immediate activation signals which are transmitted from the client to the server, but then gradient information for the training has to be sent back to the devices from the server. So we have two-way communication in that case. So again, we have then to optimize the energy consumption, the time for training. You have to optimize the overall system energy consumption, and basically we have now to find an optimal split matrix. So not just the optimal split point, but a split matrix here, how we split the various layers for the devices. So now the whole system becomes more complex. So here some layers are at the server, some at the device, depending on the features of the device. But the information we process is still the same. So we have an estimation module trying to estimate how much time it takes for the IoT device to learn and to process the model, how good is the network connectivity between the devices and the server. And then this optimization module then has to come up with these split points. That means deciding to split the model here individually for each IoT device. And here we have a setup for our evaluations. You see here two different type of devices, Raspberry Pi and Jetson Nano. And now we compare our approach, which is called ARIS, with standard federated learning, where we have a homogeneous split point, and no, we don't have a split point where all the training is done in the server, and where we have the split learning, where we have a homogeneous split point. And if we look here into the delay and the energy we use, our approach performs in most cases better. Here we are a little bit worse for a situation where we have a high power mode for the Jetson Nano device, but in most of the cases our approach worked quite well here. What is also important is accuracy. So we compare here our approach with federated learning, where we do central learning, and that's basically our benchmark. We cannot become better than that, but we are pretty close here already. Okay. The next step here is now to combine everything. That means to combine split learning and federated learning. So before, basically, we had mainly this split learning approach. Now we try to integrate federated and split learning. And there are already some related works, but our work is mainly considering heterogeneity of devices. So the so-called federated split learning approach, that's known from related work, but you see here it's only considering homogeneous devices, and also it's not adaptive, for example, in the case of dynamic network conditions. So these are the main points we addressed in our work. So that, here you see again that we can better support heterogeneity of the devices. That means in this case, we have different split points for different devices and apply this combination of federated and split learning. Again, some experiments you can have a look on in the papers if you want to have more details, but the performance now compared to related work was again not worse in the various metrics. It means energy consumption, delay, accuracy is important, how accurate is your model. Here is energy consumption, here is the delay and also the training time. Okay, a final work for the last couple of minutes. It's a little bit in a different field, but still distributed machine learning. And also the application use case we have in mind is a little bit different. So basically, machine learning, in our opinion, can be useful for autonomous driving when the car is getting data and then can learn from collecting data using different machine learning techniques. And the basic idea is now that vehicles can learn from each other. That's basically the idea, what we saw already in federated learning. So cars are collecting data, are building their model, and then the models are aggregated and the better models are computed and distributed again back to the car. So that's basically applying federated learning to such a vehicular network environment. Our idea is now the following. We try to avoid having this central component for federated learning. Since in that case, you always have to transmit your parameters towards the server, which could be collocated to a base station, for example, and then you have to send back all the parameters. The idea is, why not just communicating from one car to the other, and each car becomes a server and is a client, basically. That's the main idea, what we try to implement now. So we try to use direct vehicle-to-vehicle communication. So in that case, we don't have to communicate from the car to the server and back, but from car to car, which could be more efficient. So in that case, you only use half of the network bandwidth anyhow in that case. So we can support better bandwidth, we can support to exchange more information then, since the network capacity is higher then. And we have another advantage, privacy of data. That means there's no central server which owns all the data, but the raw data is remaining at the car and only model parameters are communicated. So the approach called distributed transport-based federated learning is using this concept of federated learning in a vehicular environment without central server, but having a distributed approach. We communicate directly between the cars, and we also use clustering. Clustering means that we try to find out which cars and which users behind the car. In every car is a user. There are different maybe driving styles and so on, and all the cars could have different data characteristics. So what we try to do is we try to cluster the cars and the users based on certain characteristics. Since if we have more homogeneous data, then also the result of the machine learning can become better. So this is basically the architecture, how we see it. It means we only have maybe some initial communication. We could, for example, initialize the car with a basic machine learning model, but then afterwards the cars only talk to each other when they meet each other. The one problem here is if we do that then the cars are in range, in communication range, only for a short time when they meet each other. In particular, if they are driving towards each other, they might be only in communication range for a couple of seconds. If they are driving behind, of course, then it's much better. So that's also something to be considered. So here you see the architecture of this solution. So basically, each car then becomes a federated learning server. So each car collects the data from the other cars and does the aggregation and can improve the own model in that case. Also, we see here this model clustering where we try to build clusters depending on different features we see in the data, which are collected by the cars. So in that case, this could be a cluster of regular drivers. This could be a cluster of crazy drivers or whatever. Yeah. So or electrical vehicles or other vehicles. So there could be different methods how you cluster these devices. This was not implemented, since for implementation we would need a couple of maybe autonomous cars, and we don't have. So therefore we had to use simulation here with some standard mobility data set from the city of Cologne in Germany, which is an open mobility data set we used, and some image data sets, which is often used for evaluating machine learning techniques, some other parameters we used here for our simulation. And here you see the accuracy, basically the machine learning model accuracy for different approaches. So our approach is the red one. This is a standard federated learning, the blue one. Here we are now better because we used this clustering approach. So we basically cluster the different cars with similar data, and then we can have a better training and learning effect, and therefore we are even better than the standard federated learning, which does not do this clustering. Also, accuracy, you see here, now our approach is the green one. We were better than the other approaches. Okay, that brings me now to the end of approximately 1 hour. So we have talked about distributed machine learning, the split learning, federated learning, compared to the rather centralized approach we have in most applications today. And I hope I could give you some examples where such distributed machine learning could make sense, in particular in the Internet of Things environment. So machine learning is moving towards such distributed approaches. We have seen that processing at end devices has some advantages and disadvantages, but we think that a good mix of processing at the user device or the sensor and at the server can have some benefits in terms of privacy, in terms of energy efficiency, and so on. We have seen that we have developed some optimization modules. I have to say this is not quite trivial. There's still some work in order to improve. Although this is per se quite computing intensive, but to some extent it's feasible. Outlook also maybe with some thought in mind that maybe somebody might be interested also to collaborate with us. So we just recently got approved 2 new projects. The left one is a European project with a couple of industry partners we see here. The topic is there that in 6G, of course 6G is also a big buzzword, but 6G is very, very broad. And one aspect in 6G, what people have in mind is that there is more and more machine learning involved in a 6G network for different tasks. We have seen at the beginning that, for example, we could try to predict where users are moving. That means all the mobile network providers, they have an amazing set of data. They know everything about you and your device, where you have been, what you communicated, and so on. And that kind of data can also be used for optimizations, for predictions, for different optimizations inside the network, but also for applications. And now the question is how to intelligently integrate such machine learning components into a mobile network provider architecture. Since today's networks, if you are familiar with 4G, 5G, we don't have machine learning components. But now we need machine learning inside the network. You have to collect the data, you have to do the training, we have to do the predictions. For example, when we talk to our mobile network provider for the mobility prediction, and we came up with the idea, they did some calculation, and then they said, if a new customer comes in and we observe the customer and collect the data, and we want to train a model for the customer, that probably takes us a couple of days with one machine. And if we have 1,000 new customers per day, then we need so many resources. So we have to think about how all this machine learning can be integrated into a 6G network. A related topic is a project we start now with Northeastern. There we have a very narrow use case for machine learning. So basically, the Northeastern people, they are physical layer people. That means they are dealing with radio signals and massive MIMO systems. That means multiple antenna systems. MIMO means multiple input, multiple output. That means we have multiple antenna for receiving and for transmitting. And in such systems, we also have to, well, we can solve some issues with machine learning, since the problem there is we have multiple antennas for transmitting and receiving, and we have to find out how we have to process the data when it's coming in. So there are different combinations. Antenna 1 sends a signal to antenna 1 to 2 and so on, and antenna 2 is sending a signal to all the other antennas, and then we receive a mix of signals, and in the end we have to find out what kind of data has been transmitted. Right now we are using pilot signals, so pilot signals are sent, and then we can learn what are the characteristics of the radio environment. Here we want to use machine learning for these massive MIMO systems. So we are not talking about just 4 or 8 antennas, but rather 64 or more than 100 antennas in such a MIMO system. And of course, this is a technology for 6G too. So we have one particular topic here which might also fit into this more wide project. And that will be supported by the Swiss and the US National Science Foundations. And I'm looking for 4 PhD students for both of these topics. That means two here and two there. So if somebody knows a good PhD student, please let me know. Good PhD students are a very scarce resource, as you know. Yeah. Okay, that's it so far. I hope you understood some things and that you found it somewhat interesting, and would be happy to receive some questions. Maybe we can discuss it now or also later among us. Then thank you.
¿Preguntas? Javier.
No, thank you. Thank you very much for your presentation. Very, very interesting topics. I was surprised every time you mention IoT, immediately after you mention machine learning. And every time you mention machine learning, every few words you mention IoT. I have like a philosophical question. Who is more important in this relationship? IoT data, raw data coming from IoT devices, or machine learning models? Who needs more the other? Can IoT survive without using machine learning models? Or can machine learning be successful without relating to data coming from IoT? Or is this the perfect relationship? I don't know. What's your opinion?
I think it's a good relationship, since in the IoT we expect the production of a massive amount of data. And personally, I had some experience recently when I was visiting University of Panama. One of my colleagues, he gave a tutorial about programming sensors. And I mean, my last programming project was some years ago. Unfortunately, I don't have too much time. And then he taught us how to use a tool set for classification of objects using a Raspberry Pi. And it took us half an hour to do that. But basically what we did, we took the Raspberry Pi, we took pictures from different objects, we labeled it. So it was only 3 objects, a key, a mouse, and I think it was an apple or so. And then we took the pictures, labeled it, took the data, loaded it up to the server. The server automatically created a model, did the customization for the Android device. We downloaded the model, and then we took the device and took pictures of other objects, and the software told us, this is this object, this is this object, this is this object. I didn't have to program anything. I just collected the data. The programming environment did everything. Of course, what I have to say, the accuracy was not tremendous. The accuracy was only maybe 70–80% with 3 objects or so. But it showed to me that this seems to be a very, very good match of topics. We have the data. We can learn a lot from the data. We can. If I would have to program that object recognition, probably it would have taken me a year or so to do that without the data. I think, and we can learn from the data and come up with solutions much faster.
Thank you.
Thank you again for your presentation. I have a question. How do these machine learning models handle fault tolerance when getting the data from the IoTs?
Good question. Just an answer how we try to solve it. So basically, fault tolerance is an important topic, and here you see, for example, outliers. That means these are some things we have to filter out, and this clustering approach I discussed also helps us to detect certain outliers and ignore then these data for the training process. That's at least one area we were active, but probably there are many more other issues with fault tolerance. I mean, the accuracy you saw, we were already happy when we reached 80–90%. I mean, in certain applications, health, probably accuracy of 90% is not really good. But I know, for example, from other people in medicine, that systems, machine learning-based systems to detect certain types of cancer are better than doctors today. That means it's better to give a picture to a machine than to a doctor, since the machine better detects a type of cancer than the doctor sometimes.
Thank you.
And I mean, there you also have a reliability issue then if humans are involved. And yeah, one of my PhD students working in the logistics area, he's currently planning an experiment where he wants to show that machine learning based systems are much more efficient and better than any humans. So there are certain areas where it's difficult for humans to compete with machines, but on the other side, it's already philosophical. I mean, probably we need still humans to have the overall supervision to decide, is the machine doing plausible decisions and all these things. But I think this is also a very active area of research, also related to explainable AI, that you really can explain somehow what your machine does.
Thank you very much for your talk. I'm from the area of control, fault tolerance and safety. There are two words that for me, for the world now are very important, is safety, security, and resilience. How do you insert this very important concept in all these architectures? Because I don't see that this is safe. If this is security, there are two things, security and safety. And how do you recover, or how do you assume that you can recover to the normal condition when there is some fault?
Good question. No, we are not maybe really focusing on that right now. I mean, yeah. I mean, it's the same as before. I mean, there are certain examples where machine learning definitely can help, where the accuracy is better. But of course, I also mentioned that when the health of people is involved, 90% accuracy is not good enough. But at least maybe the machine can suggest something which in the end the human has to decide. It always depends. Yeah, based on the experience, based on also what the research in explainable AI wants to do. That means that the machine learning model is not considered as a black box, but that some insights are learned, how the model comes to certain decisions and so on. But this is also a very active area of research, but very dependent on the application area, I would say.
I have a question concerning this .fl approach, concerning the autonomous driving example. I would think that it's always the goal to have one big central model that's the most intelligent. And so I understood the previous approach where all the cars send the data and then to the big model at the server, and then the cars get updated with a more intelligent model. So I didn't understand this approach where the cars don't send, where there's no central big model.
Yeah, so I mean, in one extreme, if you don't have this device-to-device communication, then each car would send all the model parameters, for example, to the server. Everything has to be sent here, and everything has to be to be sent back. It means the problem then is we have two-way communication here, and so that means we have to send the model parameters here and send it back. In this case, we only have to send it from here to there. And then basically the client can learn from that data. And even if we would exchange the data between them via a base station, for example, then it goes up and down. Then we also have less bandwidth in the end. So direct communication is much better than having a base station in between. I mean, for example, if we talk to each other via the base station by voice, your voice goes to the base station, goes to me. So it traverses the network twice. Here it traverses the network only once. So we have a much higher capacity than available for the data transfer. So we basically double the capacity in this case. Of course, the downside here is this car only learns about data from other cars it encounters. So it has in the end less data than if we transmit everything to a central server which could collect everything. That's the downside. But we show here with this clustering approach and some other optimization techniques that this approach might be feasible.
Okay, thank you. So every car runs on a different model, so every car behaves differently at the end of the day, right?
They have the same standard neural network, but the weight parameters are different because of the distributed learning, and the different weights are then in the federated learning sent to this aggregation server, and then they are sent back. Here we put the aggregation server in each car, so each car itself does the aggregation. It collects the data from other cars and does the aggregation itself, and then the parameters stay at the car. Also, we don't have to send it back to the others, then the others get the data also. So this second step of the communication can be saved then. But again, the data each car collects is less.
Okay, thank you. And you also, or I think you showed a slide where you compared the two approaches, right?
So this is our approach. This is a standard federated learning. And this is another approach which has a similar idea as ours, direct communication, but they don't have the clustering, for example. So this data clustering helps quite a lot. Because of that, the green is always below the blue, since the green is more or less a distributed implementation of federated learning. Here in our approach, we have some additional techniques which help us to become better. Since if we only would use the same techniques as federated learning, we could not become better. Yeah.
Okay, thank you. So you reduce the bandwidth by a lot and also increase the accuracy, so that's pretty impressive of that approach, right? If I understood. Okay, thank you.
¿Alguien más? No, pues finalizamos. Muchísimas gracias al doctor Braun y muchas gracias a ustedes.
Okay, thank you. Thanks for coming.